Hello, geologist. Welcome to Section 5, Igneous Rocks. One of my favorite types of rocks are igneous because they're so just awesome in terms of how they're made, what they do, their personality. And we're going to learn all about igneous rocks today. Hopefully, you'll come away with a good understanding of igneous rocks in their two basic categories: intrusive/plutonic, and the second group, extrusive/volcanic. And then you'll also come away with a knowledge of the four different chemistries that are associated with igneous rocks. What you're seeing in this picture is a shot I took from a helicopter in Hawaii of an active lava flow. So this is lava, and in order to have a volcanic eruption, you're going to have some source of magma from inside the earth. While that may seem obvious, it's not to everybody. And so I want to take that moment to share that with you, because just like the plumbing, when we think about our bathrooms and our toilets, it goes somewhere, right? So does our shower water, so does our laundry water. Well, the source of magma is from inside the earth. The question becomes is how deep within inside the earth, because that's going to make a difference as to what flavor of magmatic material you're going to have. So let's get started and share with you about igneous rocks today. So magma and lava, how are they similar? How are they different? Both magma and lava are molten rock, so they fit the criteria of igneous. Igni meaning molten fire. So igneous rocks must be molten to qualify. If they're not, then they turn into a different type of rock. So there are two different places that igneous rocks crystallize and cool. One is inside the earth as magma. If that's the case, it'll end up being a plutonic or intrusive igneous rocks. Those two terms are synonymous. If you have lava that crystallizes at the surface, then you're going to have an extrusive or volcanic rock. So let's look at this image here, and you're going to see where there's a red active magma chamber producing a lava flow. This feature right here is called a pluton. And plutons come in a variety of shapes and sizes, and each are unique in terms of the features that can be seen after they solidify and crystallize as an inactive magma chamber. To be frank, so much of the igneous rocks that we have in our Earth's crust and even at the surface is this stuff right here. The stuff that cools way beneath the surface of the Earth, and occasionally we get some that cools above the surface of the Earth in the forms of volcanic necks or dikes that were shallow and sills and laccoliths that have been eroded down to. And occasionally we get volcanic eruptions. But more often than not, you're going to have active magma chambers that do not create volcanic eruptions. They simply cool beneath the surface of the earth. So I mentioned to you in minerals that we talk about Bowen's reaction series. If you have not read Section 5, now is the time to stop this video and read it, because you need to be familiar with the chapter before we go through this. Then watch this thing and follow along in the book with the different diagrams and the different descriptions of the various types of igneous rock chemistries. So Bowen's reaction series is a process by which minerals crystallize at different temperatures. We can do this same process in a laboratory setting as well. Now, what I'm saying is, if you look at this 1400 degrees Celsius over here, that's a really hot temperature, and temperatures typically don't exceed that in magmas these days for Celsius, but they did a long time ago in the Precambrian eon, back when we had a much hotter inside Earth. So we created rocks that were more like this and then continued on into the 1600 or more degree temperature range. Those were called ultramafic rocks. We'll get to them shortly. So if you see these minerals here, these are your darker minerals like pyroxene and biotite, and olubine's almost it is ultramafic, but it sits on that boundary marker today of being between mafic and ultramafic. Down here where you see quartz, muscovite, and orthoclase or feldspars, you can see their temperature is much lower on the Bowen's reaction series. Over here you see the mafic, intermediate, and felsic category. Well, these are the chemistry groups, minus the one that we don't make very often today called ultramafic. And if you'll follow this over, mafic comes all the way over here. You can see it's about 1200 degrees. So it ranges from literally about 900 to 1000 degrees to 1200 degrees C. Intermediate is a lot cooler, so it's going to be in the 900-ish degree temperature setting. And then you get into felsic, and you can get as low as 650 all the way up to 800 or so degrees Celsius. My point is this. If I have felsic minerals, they're going to require lower temperature magma chambers in order to form. So if I have a really, really hot magma chamber, let's say like the one that's under Hawaii, then we would be forming more minerals that are in this section right here. So going back to the minerals lecture, all minerals crystallize and melt at different temperatures. So that's why if I get olivine in a lava or even in a magma chamber, if the magma chamber is about 1200 degrees, that olivine will not remelt because it requires temperature of around 1400 degrees or more to melt it. So it'll just float around in the magma chamber until it comes up in a volcanic eruption. And that thing, sure enough, happens. That scenario is very real. The chemistry of igneous rocks boils down to the Bowen's reaction series and understanding that minerals all crystallize at different temperatures. The mineral composition or the chemistry of molten rock changes as rock layers are melted and or minerals are melted. So typically as a pluton is coming up towards the surface, it's consuming what we call assimilates, new material as it melts, and it blends it together. So magma blending is kind of the secret behind why volcanoes behave differently and why eruptions are so variable. So I'm going to use an example from my prior days as a bartender and explain that when you were serving drinks, if someone came up to the counter and asked for a margarita, there was a recipe book in the back that we had to use to mix up drinks. And so if someone said, I just want a margarita, the first question would be, well, what kind would you like? I don't know. What do you have? And we'd go through the spill of, okay, do you want it on the rocks? Do you want it frozen? Do you want top shelf? I mean, this laundry list of things and flavors and certain quantities of these flavors that changed the actual beverage that they were getting. So someone actually came and ordered a very specific type of margarita. Boy, that made my day. I was like, yay, somebody knows and is asking for a specific thing. So that's kind of how igneous rocks are. They're like types of margaritas. And just all have one thing in common. They're made out of molten material, so they're made out of the molten margarita stuff. But the flavor changes simply based on the mineral concentration that's in each type. So we have felsic, intermediate, mafic, and ultramafic. So let's kind of look at this chart. You have a similar chart in your book, and I'll be using it a little later here. These are mineral percentages. So K feldspar refers to potassium feldspar. Notice that it's kind of a pink color. So we only make that pink color in granites and rhyolites, as you can see, because it ends right here. Quartz can be made in all felsic rocks, and then some in your closer to this boundary marker between felsic and intermediate rocks. So I'm going to call that high silica intermediate rocks. Then you're going to see these darker minerals like biotite and some of your other darker minerals can be formed in felsic rocks, and they progressively get more so in intermediate mafic, and then of course you're going to get ultramafic over here. All right, so with that in mind, there's also a temperature correlation. So the temperature is much lower for felsic than it is for intermediate. Intermediate's lower than mafic, so mafic's hotter, and then the hottest molten material is ultramafic. So that all matters to the type of margarita mix that you're going to get. So In each case of felsic, intermediate, mafic, or ultramafic, if you look down here, there's an intrusive and an extrusive rock that matches for them. In other words, you can make the same chemistry of felsic rocks, but you can have one that cools inside the earth, and it usually takes million plus years to do, or you can have something that cools as lava in days and hours, and that would be your extrusive. So another term for intrusive is plutonic, and then another word for extrusive is volcanic. So we're going to be looking at these different sets of rocks because they match, and they are the intrusive and extrusive equivalents for each one of the major chemistry groups of igneous rocks. When felsic chemistry, why is it such a special type of igneous rock? Well, felsic probably is the most famous in terms of countertops because people like to buy granite countertops. Let me caution you, before you buy granite countertops, you may not actually be buying granite in all cases. So when you get into the darker colored, you're probably dealing with another type of intrusive or plutonic igneous rock. Remember, those terms are synonymous. Intrusive and plutonic means magma inside the earth, and extrusive and volcanic means lava that's cooled above the surface of the earth or at the surface. So in terms of felsic chemistry, one of the key things is what percentage of silica each of these chemistry types has. And in the case of felsic, it has greater than 65% silica. That is a guaranteed test question. So when you have the extrusive or volcanic felsic igneous rocks, you're going to have a form of rock called rhyolite. This is rhyolite up here. Now, rhyolite comes in a very, very light shade of gray, pink, almost white colors. There's a variety of them, from pumice to volcanic tuff to volcanic breccia. So there's a variety of forms of the rock rhyolite. But notice, even though it has some bumps and stuff in it, that's because it's pyroclastic in nature, this particular sample is. In other words, it came out of an explosive volcano. Compare this to that. And notice that you can see the individual crystals that have grown up next to each other. This rock does not have that. In a little bit, we'll be talking about texture. This one has what's called phaneritic texture. This one is aphanitic texture. So this is your intrusive and plutonic igneous rock that's felsic, and it's known as granite. So granite is simply a margarita mix of a variety of felsic minerals, high in quartz and potassium feldspar if it's pink granite. In this case, that's pink. Sometimes you end up with a white and black granite, and that means it doesn't have the potassium feldspar. It has the orthoclase instead, like plagioclase feldspar. And the black is the biotite. So these are all the minerals that you would expect to find in felsic igneous rocks. So let me be transparent about the explosivity of the different types of volcanoes that contain these chemistries, and I'll do this for each type of group that we come to. For felsic, the temperature is very low to form quartz. So if that's the case, you get, if this is the neck, or really an active volcano, it would be the pipe of a volcano, and you've got quartz that's crystallizing because your magma is around 700 or 800 or even 650 degrees Celsius, you're going to have polymerization, which is crystal making in short. And so it's starting to develop a plug inside of that volcanic pipe. That means all of the gas and ash and magmatic material is building up behind that plug, and it takes an immense amount of pressure to blow it out. So when it does blow, felsic chemistry types of eruptions are highly explosive, by far the most explosive of any type of volcano. That seems a little backwards because it's so low in temperature. So I need you to kind of wrap your brain around that lower the temperature of magmatic material, the more violent it's going to be when it erupts. So the colors of felsic igneous rock typically range from white, tans, grays, and very light shades of grays, and pink. Those are the major colors that you're going to see. Of course, you can have the biotite, which is the black material, but that's not what makes up the matrix or the ground mass of all of these rocks. They're very light in color. So the light in color corresponds with the also lighter in density and also lower temperatures. So moving into intermediate chemistry. Well, If you recall, felsic rocks had greater than 65% silica, and they're the most explosive eruptions. So if intermediate igneous rocks have between 53% and 65%, there's a broad range of variability in terms of how explosive a volcano could be. So the closer the magmatic material is to 65%, that's intermediate in chemistry, the more explosive that eruption will be. Also, the lower the temperature will be and the lighter the color of the rock material would be. The closer you get to 53%, the hotter the magmatic material will be, the darker the shade of gray will be, and then the more fluidy material it will be because it's hotter. So the joke is that intermediate rocks are literally like 50 shades of gray. They come in all different colors of gray. Sometimes you can even get such a dark gray it begins to have a black color, not pure black, but a grayish black, and that would be your 53 percenters. So the extrusive and volcanic intermediate rock would be andesite. This is andesite up here. Notice how gray it is. Now I see some crystals embedded in it, but they're not connected like puzzle pieces. So if they are, that would be an intrusive rock, but this is not. This is a volcanic. So my description of olivine a few minutes ago in the Bowen's reaction series, how it got hot enough to form these minerals right here, but never hot enough to remelt them, that was the case in this igneous rock right here. Well, when you get something like a diorite, you need a good light on this and having a hand lens to see that this has interlocking crystals where they are bunched together just like granite. They're just a different recipe, so the different colors vary. And diorite is what the intrusive or plutonic intermediate rock should be. So now we're making it to the mafic category. So mafic rocks are dark. It's possible that they could be close to that top end of mafic, which is 52%. They might be borderline a really dark gray. But most of these are black in color. So keep in mind that the lower the percentage of silica, the hotter the magmatic material will be in order to crystallize those minerals. So the 45% versus the 52% would produce a more violent volcanic eruption, but not nearly as much so as your higher silica intermediates and felsic. So this is a dark piece of basalt. It's black. There are no interlocking crystals, and you can see the interlocking crystals here. I tried to put a good light on it. It looks bumpy to you in this picture, but it's called gabbro. This is the intrusive and plutonic rock of mafic. And so it looks just like granite, but instead of having the cute pinks and whites and tans and grays, it's a dominance of black crystals that are interlocking like puzzle pieces. Well, you're not going to see that in basalt because basalt cooled off at the surface, so it cooled off fast in days. So it didn't have time to create crystallization of these larger crystals that can grow together that make intrusive or plutonic rocks. Well, there's still a fourth chemistry. It's called ultramafic. So what's ultramafic mean? Ultramafic refers to any rock that has less than 45% silica. The truth is, there are very few magma chambers today that can produce this type of magmatic material. There's a handful of lava eruptions that happen in Hawaii and a few other places in the world that come close. And they may even have a hint of being ultramafic. I will tell you, though, that lower mantle in particular is ultramafic in chemistry. It's just that as you get closer to the surface of the Earth, the temperature decreases, so it's just not hot enough to create and crystallize the minerals that make up ultramafic rocks. Olivine is the main chemistry mineral that's created. So there is an extrusive and volcanic lava rock that is ultramafic called komatites. And while this picture doesn't show its kind of greenish dark black color, it really is, I promise you. And then this is your peridotite down here, and a special type of one at that, where you can see just a dominance of the green crystals. So ultramafic rocks are beyond black. They have black and a dominance of green in them. So like I said, most of our ultramafic rocks, especially lava ones on the surface, have been changed because they were so old, they happened back in the Precambrian eon, that they've been altered typically by metamorphism. Occasionally, though, you might get a volcanic eruption that produces quite a bit of olivine. So that could be stuff that crystallized in the magma chamber, then came up in the magmatic material like olivine. So there's a rock called olivine basalt that you'll be seeing in lab that I'll show you pictures of. And if you're in my face-to-face class, you'll actually get to see the sample of it. But that has these olivine crystals that sit in the rock, and they're little gifts, kind of like our andesite that was porphyritic that had little black crystals in it. Well, it's the same kind of thing. They're not interlocking, so they're not intrusive. It's just they were minerals that couldn't be remelted. So those are the 4 chemistry groups. Let's kind of analyze this ultramafic and say, let's just by happen chance we get a volcanic eruption that's ultramafic. Well, it would be very runny, and it would be super hot, and it would be the least violent of the 4 types because it is so hot. So with mafic and ultramafic eruptions, I would expect to see lava fountains and lava lakes and lots of lava being poured out as rivers away from the volcano, as compared to intermediate, where you're going to have some explosivity, and certainly the closer you get to 65%, they become very, very violent. So you'd have a lot of ash, you might have some lava domes if you have an intermediate close to 65%, but by the time you make it to felsic, it's going to be like a sheer disaster pyroclastic eruption, mega type of these bad volcanoes, super volcanoes like Yellowstone. So those would be your felsic types of eruptions. Now, let's bring us into the textures. There are 2 texture terms associated with each major rock group. So there's 2 for igneous, there's 2 for sedimentary, and there's 2 for metamorphic, and they do not cross over. In other words, I can't apply my texture terms from metamorphic to igneous, nor can I apply my igneous to metamorphic or sedimentary. So the 2 terms for igneous are phaneritic and aphanitic. So what do the 2 terms mean? First of all, texture is determined on how the igneous rock crystallized and cooled off. So just keep in mind that rocks that cool beneath the surface will take years, and literally tens of thousands, if not millions and millions of years to cool off, especially the deeper the magma chamber in the surface of the earth. So if you have one that's 50 miles beneath the surface, it's going to take a lot longer to cool off than if it was just 2 or 3 miles beneath the surface. The other part to that would be how big is your magma chamber. And when we get to the igneous plutonic structures in a little bit, batholiths, beginning with like a bathtub, batholith, these are the largest magmatic plutons, and they can cover an entire state or more. So these things, if they're that large, will take even longer to cool off as opposed to a small little dike or sill that just may be a couple of centimeters wide to 10 centimeters or maybe even a couple of feet wide. So all of that factors into what kind of cooling situation happens beneath the surface of the earth. At the surface, though, you're looking at days, maximum of weeks, and certainly in some cases hours, where these rocks begin to crystallize and start to harden and cool off. So the longer you have to form crystals, the larger they're going to be, and the more of them they're going to be. So let's start with phaneritic texture down here. Phaneritic texture looks like puzzle pieces that are interlocking. So when you look at phaneritic texture and you feel a rock that, like granite, that's phaneritic, it is going to be dense and heavy for its size because those crystals have grown all the way through the rock. And so if I change the color maybe of this to pink and this one to white, this one is a little black biotite, here's another pink crystal, here's another pink crystal, here's a white, here's a gray, here's a black biotite, here's a pink, you get my drift. We can just color these in, and if I made that pink granite, each of these crystals would have grown together against each other as puzzle pieces. So the way I remember phaneritic texture is P for plutonic, P for puzzle pieces. So this is only going to apply this type of texture to intrusive and plutonic rocks. So granite, diorite, gabbro, and peridotite will all be intrusive and have a phaneritic texture. So those are the four major groups. So anyway, moving on into aphanitic. Aphanitic refers to rapid cooling, so there's limited time to form crystals. And at that, the crystals will be really tiny if there's any that do form. So aphanitic, the way I remember this, is A for after the eruption. Now this diagram shows a background that's gray. I can change that to pink, I can change that to white, I can change that to black, I can change that to green, which will subsequently change the margarita mix, which will change it from either felsic to intermediate to mafic or ultramafic, right? The point is that there's none of this. There's no interlocking crystals. And aphanitic applies to all extrusive and volcanic rocks, because remember, extrusive and volcanic are synonymous. Unlike phaneritic, which there's just one definition for that, there are multiple types of aphanitic, what I call subtextures. So there are special characteristics of a particular rock. So let's look at phaneritic texture up close and personal. It looks like a jigsaw puzzle. Can you see that? Here's a pegmatite, a type of granite, and you see these big giant crystals and how they're grown all the way through the rock. Well, that matches what this is over here. So zooming out, that's what your granite's going to look like right here. So if you pick this piece of granite up, even though it's about this size, it is a very heavy rock. And it's because those crystals have grown all the way through the matrix or ground mass, which is the background of that rock. So that's important. Phaneritic rocks always cool slowly beneath the Earth's surface. And in your mindset, I want you to think millions of years to cool off. So which one of these is aphanitic and which one is phaneritic? So you're looking for interlocking crystals in order for it to be phaneritic. So if you chose this one over here, that is phaneritic, and you can actually see how the white and black crystals have grown up next to one another. And then you have a very light colored knot. You don't see this at all. You just see a background. So it kind of matches this right here. So that's an aphanitic texture. And this happens to be andesite. This happens to be diorite, which are both intermediate rocks. This is just the extrusive version. This is the intrusive version or plutonic version. All right, let's talk about aphanitic texture. This is the extrusive volcanic igneous rock. They do not have interlocking puzzle pieces. So these rocks have a fine-grained ground mass, and ground mass refers to whatever the main background color is and character of that rock is. So they cooled very quickly, usually in days and hours, maybe weeks, depending on how hot the material is. So if we take this background right here, which is just an intermediate gray, put it on this one's getting close to being probably at that 64-65%, so it's still intermediate. But do you see these little rocky road chunks here? Well, that's a special mineral, that's a mafic mineral, and that just didn't have time or temperatures enough to remelt them, so they stayed in the magma material, and when it came up as a lava, they floated in the lava, and as it cooled, these are the little gifts that are there. The key is these are not interlocking. So sometimes we get an aphanitic rock that looks just like this, where there's absolutely no crystalline structure at all. Like there's no individual crystals, it's just a lava rock. It's kind of plain Jane. Oftentimes we get a situation that looks like this, where you get what are called phenocryst. And we'll get to phenocryst here shortly. So remember I said that aphanitic has subtextures. There are 4 to be exact. So I had a roommate in college who exhibited all of these subtextures in her personality at one time or another. So I'm just going to call her Jane Doe. So we'll call her Jane for now. And so Jane was beautiful some days, and she was glassy. Glassy has this gorgeous look to it. This is obsidian, so very shiny, very, very beautiful thing. And lots of people, this is their favorite rock, is obsidian. So glassy subtexture, how does it form? It is not an individual crystal. It is actually volcanic glass, so it's instantaneous cooling. So whenever you see glassy subtexture, you should be thinking, man, there was rapid cooling, like instantaneous cooling. So glassy subtexture is one of the best examples of aphanitic texture I can give you, and it always happens extrusively. Sometimes my roommate Jane would get a little airbrained, and she would have holes, and she just wouldn't make much sense. Maybe you've experienced that. I certainly have had days like that. Well, these little pocket holes here, these little vesicles is what they're called. These are little individual gas cavities. And the gas cavities still retain their shape in the rock after the rock crystallizes. So this is a piece of oxidized basalt that is just very vesicular. So vesicular means it has gas cavities, where you're going to have those gas cavities at the surface. You're not going to have them deep inside the earth because you're involving oxygen here and other types of gases that fill that space. So on a rare occasion, my roommate Jane might actually have a pyroclastic moment. So what does pyroclastic mean? Pyro, fire. Clastic is a sedimentary term that refers to rocks and fragments of other pieces of rock. Pyroclastic refers to a very explosive volcanic eruption event. And so you would have had massive amounts of ash and volcanic bombs and volcanic debris and pyroclastic flow material coming out like ash and volcanic tuff and volcanic breccia and pumice, which is all of this stuff right here. So this is a volcanic tuff. And you can see all the fragments of material that blew out of that volcano that have been literally seared together and crystallized as a rock. This is rock solid now. This is pumice. A lot of people are familiar with pumice. It floats, by the way, and it also, do you see its little gas cavities? So it's also vesicular. And believe it or not, most pumice has a lot of glass to it. And so if you get it under a microscope or a hand lens, you can see its glassy subtexture as well. It just doesn't have the same beautiful glassy subtexture that most obsidian has. Nevertheless, these created or were made in a very highly explosive situation. So if you have pyroclastic subtexture in volcanic rocks, that means that you had some kind of big violent volcanic event. So the more mafic and ultramafic that igneous rocks become, the less that you would ever expect to see pyroclastic subtexture. There have been some examples of mafic igneous rocks that I've seen pyroclastic subtexture with, but it decreases as you get hotter and hotter in temperature because this stuff remains molten. All right, what does porphyritic mean? Let's say that again, porphyritic. It's a mouthful, porphyritic. How is it different from phaneritic? So this type of subtexture has what are known as phenocryst. Well, phenocryst would be like this thing, this. They're little crystals or even big crystals in this case, but they are not interlocking. So if you have interlocking crystals throughout the entire matrix or ground mass, the background of that rock, remember that rock would be very, very heavy. Porphyritic does not have that. Instead, the crystals have not been remelted and they were in the lava or magma as it cooled. So porphyritic subtexture can, in some cases, can be applied to phaneritic rocks. In our course, we will keep them separate. We will keep them in aphanitic category and not phaneritic. But I did want to address that because if you become a major, you're going to go, well, I think she said it only happens in extrusive rocks. Well, there are some descriptions of rocks that are so close to being phaneritic that they can actually be called porphyritic. But again, for this class, we're going to strictly make it an aphanitic, the fourth aphanitic texture type, and it refers to volcanic rocks that have these random crystals that are not interlocking. So how does porphyritic texture differ from phaneritic? So here's your regular aphanitic texture, just a fine grained background, no phenocryst. These crystals are the floating gifts that get solidified and crystallized in either plutonic or volcanic igneous rocks. But see, they don't make the entire background or ground mass. I still have that gray ground mass. Now down here I've got phaneritic texture that has that interlocking crystalline structure. So to be phaneritic, it must have that interlocking jigsaw puzzle appearance. To be porphyritic, it will just have some crystals here and there that are not completely consuming the entire mass of that rock. So getting back to igneous rock chemistry, this is the diagram in your book. So many textbooks have a diagram like this. I had them make a few adjustments to this diagram when we published it because I wanted to be sure that this became clear. So phaneritic texture is going to always apply to granite, diorite, gabbro, and peridotite. Aphanitic texture will always apply to rhyolite, andesite, basalt, and comatites. So let's see if we can read this properly. Felsic rocks. Here's all your felsic minerals. Here are your intermediate minerals, and some of those overlap, right? Then you get into your mafic minerals and then to your ultramafic. So this boundary marker right here between mafic and ultramafic is where some of our lavas are today, like in Hawaii. And you get quite a bit of olivine in there, so they kind of hover right at this marker right here. The point being is, here's felsic, intermediate, mafic, and ultramafic again, so you can see it. This is always a felsic intrusive plutonic rock. This is always a felsic extrusive volcanic rock, rhyolite. And as I mentioned earlier, there's multiple types of rhyolite. Then in intermediate, your plutonic intrusive rock is diorite, and your extrusive volcanic rock is andesite. When you get into the mafic category, the one that's like granite, that's in your dark black category, it's going to be gabbro. So it still has interlocking puzzle pieces, but it's harder to see because they're very dark in color. And then your extrusive lava is going to be basalt. There are so many types of basalt. There's pahoehoe, there is just flood basalts, there is vesicular basalt, there's olivine basalt, there's just a lot of different types of basalts. But nevertheless, they still have the same mafic extrusive background mass of black. And then for ultramafic, peridotite would be your interlocking puzzle pieces like granite in the ultramafic category, and your comatites would be lavas. And as I mentioned earlier, comatites, most of them have been metamorphosed around the world that still exist from the rock cycle, because they were very old, deposited back during the Precambrian eon when volcanoes produced hotter lavas. All right, that brings us into plutons and the different places that we can get magma that's trying to work its way to the surface. First of all, magma works its way up to the surface because it's lighter in density than the non-molten rock. And as it rises through the surface, it's going to melt different rock layers that it comes in contact. But the thing that a lot of people feel is that it must melt all of it, and that's just not the way it works. So it may, for whatever reason, may not be hot enough to melt certain minerals, and it may be hot enough to melt others, or it may consume the entire rock. It just kind of depends on the character of the heat and the hot spot that's generating that plutonic magma plume to come to the surface. So we have a source for every volcano. You have it connected to a pluton under the surface. And all plutons are connected to a granddaddy, or the biggest one ever, which is called a batholith. So we're going to talk about the difference between all the plutonic structures, how they work, and why they're called what they are. We'll start with the biggest first and work our way to the others. Batholith. Get the spelling here. It's not a baccolith with two C's, because there's such a thing as a laccolith that we'll get to in a minute. That's this thing right here. You can see it has two C's. So it matters in the spelling. Why do I really care? Because batholiths are so prevalent across Earth, and we do have them exposed at the surface that are ancient. In other words, they've been hardened for usually millions of, tens of millions, if not hundreds, or even billions of years. And rock layers have weathered down with some uplift typically that bring them to the surface. So I can think of several. In Yosemite is the Sierra Nevada batholiths. If you go up to Montana, there's Boulder batholith, and then you get into Texas, and Enchanted Rock State Park is a great example of a batholith. This is a perfect time to give you your geology moment for igneous rocks. We're going to take you to Yosemite National Park, that's located in California in the Sierra Nevadas. So what makes this particular place so awesome, besides the incredible glaciated environment, is this remarkable batholith system of granite that's been pushed up to the surface, and all the rock layers weathered and eroded down, so it's exposed. And because all the weight of all of those rocks above it have been removed, the rock actually cracked, and the big batholith, and now it's kind of literally peeling apart at the seams from something called exfoliation domes or onion skin weathering. So let's hope you enjoy this, and I'll see you back right after Yosemite for the rest of section 5. Wow, amazing, isn't it? This is Yosemite National Park. I am right in the vicinity of Half Dome, and you are looking at some of the world's best exfoliation granite domes. You can see them behind me where the big faces of the walls have just come completely off, and you're looking at literally history geologically in the making. And I want you to take a look at that rock and understand that that used to be a big giant granite batholith. And it still is today, obviously, but it is hardened and it's come to the surface. So the story about how some of this stuff broke off is why Yosemite is so famous, because there's some thoughts that Half Dome actually got cut in half by a glacier. While that might have had some impact to it, probably more likely a rock slide actually fractured the thing in half. And we've had polishing and refining of that from the last ice age with a glacier. But I want you to really notice that the walls of this granite have been completely fractured, have been completely exfoliated, and are creating mass wasting all throughout the park. So I'm going to step aside for a few minutes and let you just absorb the view, because it is absolutely incredible. And I'll take some photographs and come back to you in a minute.
Just do some deleting. I actually have it.
So you just witnessed some tourists walking by, and I'll continue on and let you know a little bit more about what you're seeing. That is exfoliated granite right there, and if you can make out how large sections of that have scraped off, they've actually slid off. I'd also make a note that you can see a lot of scratches in the bedrock. That's from ancient glaciation from the last ice age. So this area has been impacted in multiple different ways, and it's still being changed before our eyes. So welcome to Half Dome area of Yosemite National Park and the amazing power of erosion that has happened to this geological phenomena. See you at the next stop. Bye. How is Yosemite? Makes you want to go, doesn't it? Yosemite is just an incredible batholith system, and I really want you to think about the size that you saw of Yosemite Valley, and let's apply that as we continue on in our plutonic structures section of this lesson. These things are huge. They're 100 square kilometers or larger. That is a minimum size requirement. So you can bet you that's a test question, right? So their surface area they're huge. They're just a very large thing. Usually they cover regional geology, not just a small area. So let's talk about stalks. Stalks are usually small blobs. I'm going to kind of draw what I think it should look like right in here. When I had this image made, the stalk that was produced by the person that drew it, it didn't turn out right, so we just didn't get it. But they're kind of blobby shaped, most of them are. So they're smaller than a batholith, but they're bigger than any other type of like sill, dike, or laccolith or volcanic pipe. So they're the remnants of batholiths that have typically started to grow upwards, and they have a surface area of less than 100 square kilometers and usually much smaller than that. So stalks are just that. They're the leftover pieces of batholiths. A dike. What is a dike? An igneous one. So first of all, a dike is discordant. What does that mean? Discordant means it cuts across rock layers. Dike, D for dike, D for discordant. And all dikes cut across rock layers. So some people say, well, this is a dike. It actually has graduated into what's called a volcanic pipe, but dikes can go vertically up and down, or they can go sideways. I've seen them both ways in the field. They are tabular in shape. What does that mean? It means they're more table-like in their character as opposed to blobby like batholiths and stalks are. So dikes can actually come up to the surface, and they do. They can actually puncture the surface and create lava eruptions at the surface as fissure eruptions. And then the ground can actually weather down and erode down to expose ancient dikes like these right here. And you can see those like in New Mexico. Shiprock is an example of a volcanic neck, and there's a whole series of dikes that comes off of it. So dikes are very common. They range in just a few centimeters and inches in width all the way up to miles long. So you can imagine that dikes are important features for getting igneous rock from a batholith up towards the surface. What is a sill? A sill is a concordant igneous pluton. And the way I remember concordant, it's like a sandwich. S for sandwich, S for sill. It literally intrudes like peanut butter between different rock layers. So if you can think about peanut butter and jelly squishing between your layers of bread, that's kind of how I imagine sills to look like. So they are tabular in shape, just like dikes, but they are in between rock layers, so they're concordant. Laccolith. Remember, the spelling is different. It's not L-A-T-H like a batholith. It's a laccolith. Laccoliths are sills that have overgrown in most cases and started to actually grow into a much more shallow plutonic feature that's kind of mushroom in shape, so it has a dome-like top to it, and it will deform the surface when laccoliths start to form. So if you've been out towards Big Bend National Park in Texas, there's a laccolith out there. There's one out near Page, Arizona on Lake Powell. You can see a laccolith there. They're all over the world. So they're fairly shallow, intrusive plutonic features, and they're much larger than a sill. So they kind of got overgrown and have that mushroom shape to them. All right, so what's the difference between a volcanic pipe and a volcanic neck? I think it's important that you know the difference. The pipe is when it contains active volcanic material, so molten rock. And the neck is after that molten rock has solidified, because typically not all of it will come up during a volcanic eruption, if there even is an eruption, and you will get a solidified amount of material right here that will solidify, causing the volcanic neck to be rock. And typically the igneous rock is very sturdy, so it doesn't weather as fast as the sedimentary rocks around it. So you will get these features, and I can give you a great example if you want to Google it. Google Devil's Tower in Wyoming, and that's a volcanic neck. So there are 4 chemistries of margarita mixes for igneous rocks: felsic, intermediate, mafic, and ultramafic. And ultramafic's the one we rarely, if ever, make on Earth today, but we've made it in spades in terms of volume back in the Precambrian when the Earth's interior was hotter. So the lava that you see over here from the Smithsonian is called a pahoehoe. Pahoehoe, P-A-H-O-E-H-O-E. That's a Hawaiian term for smooth and ropey. And so this is black. So I'd ask you, which of the 4 igneous chemistries would this fall under? It would not fall under felsic, because those are pink, tans, grays, and whites, and very, very light shades of gray at that. Intermediates are all those 50 shades of gray, and then mafic is your super, 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 super dark grays and all blacks, and then ultramafics are black-green combination. So this is black, which would mean it would fall under the mafic category. There is very sharp and rough lava called Aa, 2 A's, AA. And Aa in Hawaiian means rough and sharp. The joke is that the Hawaiians walked out barefoot on Aa and went, ah! And it was very detrimental. I can tell you, having walked on Aa with safe shoes, it can tear your pants, your jeans, your shoes up. It's very rough stuff. So if you were to have a volcanic eruption that was like Yellowstone, the most recent really catastrophic 640,000-year-old eruption, it would have been in this category right here. Mount St. Helens would be at the top end of intermediate when it erupted in 1980. So as we progress through the semester, you really need to hang on to the felsic intermediate, mafic, and ultramafic knowledge because it changes the conversation on what type of rock was present when these were made. When it comes to aphanitic texture, I need to point out that you can have more than one subtexture in a rock. So like I even mentioned it when I said that pumice was vesicular, it had some glossy subtexture, and it certainly was pyroclastic. So you can have all four subtextures happen at once, 3, 2, 1, or even none. So there are many aphanitic igneous rocks that just have a nice plain background, and they have no subtexture to them. So this is Mount Rushmore. Let's look at its very light color, and if you got up close and personal to it, it would be black and white and with interlocking crystals. Well, that would put it in the felsic category, and the one with interlocking crystals is always granite if it is that white and dominance of those light colored minerals. And this is an important thing to contemplate because granite does weather. Even though it's very durable, it does weather, and it weathers into our soil. The feldspars in it create soil. So here's old Washington here, our first president, carved into Mount Rushmore. And, I like to point out that Mount Rushmore is not marble, which a lot of monuments are made out of. That's a metamorphic rock that used to be limestone or dolostone. This is granite igneous rock, and this is right off of Needles Highway in South Dakota. And it is a giant volcanic neck is what it is. So it's weathered out, and it's made this beautiful set of geologic formations called needles. And so Needles Highway actually makes little pigtails all the way down. It's a beautiful drive or motorcycle ride if you want to take it. So I hope you enjoy your nature moment, and I'll see you back for section 6.